Hi, and welcome to the Introduction to Phoenix Controls. My name is James Barrett. I'm a sales support engineer here at Phoenix Controls, and I'll be guiding you through this presentation. To get started, a little bit about the corporate history of Phoenix Controls. Phoenix Controls was founded and focused on mission-critical environments. We've been the system performance leader for over 35 years. Well over 1 million valves have been shipped out of our factory. Typically, we build and ship between 40 and 50,000 valves per year. And as that goes over the years, we've had well over 25,000 installations in 45 countries, and that number grows every single day. We boast the lowest life cycle cost because we have a large turndown ratio on our products and they have no maintenance. And we have a very good upgrade path with legacy products since we've had our products out in the field for so long. Phoenix Controls boasts itself on being a total critical environment solution provider. So while some manufacturers tend to provide pieces to a system, just as an airflow controlled valve or just a thermostat, we like to supply an entire system to the end user. So Phoenix Controls was really founded on our Venturi air valves, but when you think about the critical environments and where they play, there are other devices that go into those spaces. When you think about a wet chemistry environment, obviously things that control fume hood themselves. So you'll have a fume hood display, you'll have sash sensors, what we call a zone presence sensor for energy setback, as well as pressure monitoring to be able to reset the pressure inside the ductwork. We also have a full line of integration controls in our platform that we have the PCI, which is actually integrating the room level controls into the building automation system. We also offer software called Vision CE, which gives you a look into the environment, gives you trending capabilities, the ability to know what's driving your air changes inside the space to give you the best approach to set back and reduce as much energy as possible, as well as maintain your building in the most efficient manner. PC Optimizer is a tool that we offer free of charge to people to be able to look at their existing building and compare it to how much you can save in the future with Phoenix Controls. And then on the bottom here, you can see various different platforms that we have for local occupancy control of a space, pressure monitoring, as well as temperature control. So what really makes the Phoenix Controls offering unique? One similar approach to what Phoenix Controls does in regards to airflow can also be applied to water control inside of a building. Most people have heard of a Griswold water control valve when it comes to controlling a fixed volume of water inside of a building. And a Griswold water valve largely works the same principles as a Phoenix Controls valve uses. So inside of a Griswold water valve, you have a calibrated spring that needs a minimum differential pressure required to compress that spring and get that valve into its control range. And then anything above that minimum pressure will give you a constant volume of water going through that valve. Phoenix Controls valves work largely on the same principle. So if you see the pictures on the bottom right-hand corner, you can see there is actually a calibrated spring inside the cone in the middle of the Phoenix Controls valve, and that is what allows the valve to be pressure independent mechanically. It also gives us the high turn down ratio and the flexibility of the airflow control situations that we play in. So the benefits of flow metering as it applies to the Phoenix Controls valve, number one is that the valves are characterized at the factory. And that really gives you a couple of benefits. You don't have to worry about rebalancing these in the field. You don't have the guesswork of putting a K factor into the airflow control device once it's installed in the field. You know that when it ships from the factory and gets installed, it's already pre-characterized and there's no field measurement. And then we have this acronym called PAINTS. Pressure independent mechanically, so the valves are going to automatically adjust to the changing duct pressure without the need for a flow sensor and actuation to be able to try to maintain a fixed set point. We guarantee accuracy of plus or minus 5% to command, and that's across the entire pressure range of the Phoenix control valve, as well as the entire flow range of the Phoenix control valve. We have inlet and exit insensitivity, which means it doesn't matter what elbows you have in the ductwork in your building, you can install a Phoenix control in the most challenging environments and still get the same accuracy, the same controllability out of that device. There's no scheduled maintenance on the Phoenix Controls valve because there are no parts inside the airstream that will get clogged up and dirtied having to do with the control of the valve. We have a large turndown ratio up to 20:1, which is much greater than flow measurement devices have, and we guarantee the best system stability and speed of response to less than 1 second. Now, I mentioned that we don't measure airflow in the field, and that's true. However, when the valves are characterized at the factory, we do measure airflow in the factory. So Phoenix has 6 air stations inside of our manufacturing facility, and these are ISO 17025 accredited air stations. So our entire calibration process of our valves is actually third-party certified. When we calibrate the air stations quarterly, we actually use NIST traceable devices, and that picture you see on the right with the orange ductwork is actually showing you how we calibrate the air stations. So there's a fixed Venturi tube that has a known flow at a given pressure, and we actually set those up on each one of our air stations to guarantee that the air station is accuracy before we actually calibrate the airflow control valves. So in addition to that, we also had a third-party certification called the NVLAP, or National Voluntary Lab Accreditation Program, certify our air stations to guarantee the accuracy of the Phoenix products. So when we build and ship our valves, you have peace of mind knowing that the products are going to be plus or minus 5% because it's third-party validated. The characterization of the Phoenix controls valves, again, I mentioned it's guaranteed across the entire flow range and pressure range of the valve. And the way that is achieved, when we characterize the valves at the factory, and we do characterize every single valve because every valve body has slight difference anomalies in it. Every cone package and spring has a very little bit of difference in them. So we value characterizing every single valve. But when we're testing those valves, on the valve has 48 positions from min flow to max flow. But when we're testing the valves, we're actually testing more like 192 data points across the entire flow range. The reason we do that is we know when our valves get installed in a building, they're not going to be running at one differential pressure all the time. We know that they're going to be running at a various different amount of differential pressures. So at every single flow position across the entire flow range of the valve, we're testing at multiple pressures, and then we're averaging those points to get the accuracy across that full flow range of the valve. Now, when it comes to mechanical pressure independence from the Phoenix controls valve, I mentioned that that pre-characterized or that pre-calibrated spring is inside the cone inside of the valve. So let's look at how that functions. As the differential pressure decreases across the valve, the cone is going to come out of the Venturi, giving you a larger area around the cone. The velocity drops off, but you're going to get the same net airflow. And conversely, as the pressure increases through that valve, the cone goes down into the Venturi, the area around the cone decreases, giving you a higher velocity, but you get the same net airflow. This is based on Bernoulli's principle and the function of a Venturi inside of a measurement or a control device. Now, taking into account that 48-point flow curve that I mentioned earlier, now that we can take the differential pressure out of the equation, we can look at the position control of the valve in a completely separate control loop than what you would have if you were trying to measure flow and control that valve based on the varying differential pressure through the valve. So now that we know the pressure is taken out of the equation, you can easily position the entire drivetrain of the valve based on that 48-point characterized curve. And that's going to give you not only a quicker speed of response because you're going to a known set point, but it's going to be 100% repeatable, and we can guarantee that our valves don't hunt based on trying to find its set point due to changing duct pressure conditions. Inlet and exit insensitivity inside of a building is important not only for a new building, but also if you're trying to do retrofits. So for a new building, these are some pretty challenging installs where if you're trying to get a straight duct run to measure airflow, it would be very challenging. So this is a 180-degree bend inside of a ductwork. Obviously, not really a good place to put a flow sensor inside that installation. Here's another challenging installation where you have valves mounted vertically directly off of fume hoods. And in this particular application, there's such a short run of duct between the fume hood and the main exhaust riser, there's absolutely no way that you could put a flow sensor in there and get any relative accuracy to control that airflow. This is about the worst case scenario you can get, where you have your main duct riser with a 90-degree bend into another 90-degree bend with a splitter going into 2 Phoenix valves, one with a 90-degree bend going through a hard ceiling and the other one with 2 45s going through a hard ceiling. Again, there's not enough straight duct between the valve and the riser to be able to get a good flow measurement. And then who hasn't seen a scenario where the pipe fitters come in, put all the water pipes in the building, and then it's up to the sheet metal contractor to make sure that the valve connects up to either a diffuser in the ceiling or to a fume hood in the room. And sometimes you have these, crazy snake bends in the ceiling. So we've all seen these type of installations before. And again, none of these affect how the Phoenix controls valve work because we have pressure independence mechanically, and based on Bernoulli's principle, the way the airflow goes through the valve, it is unaffected by elbows inside of a building. There's no scheduled maintenance on Phoenix Controls products, which for a building owner gives you reduced downtime, a reduced maintenance budget, which, as we all know, there may not even be a maintenance budget. A lot of times, more and more frequently, they only do things reactionary. So if something breaks, they go out and fix it. They're not planning ahead to go out and clean flow sensors and recalibrate things. They're just going based on if something breaks. But one thing that we do recommend, even though you don't have maintenance on a Phoenix product, we do plan annual or semi-annual audits with your health and safety group if required, again, just to go into the Phoenix system, manage everything on the network, make sure all the devices are communicating. And if you did have situations where something like a sash sensor on a fume hood broke, you could definitely look into that and fix it before it becomes a real problem. But the products themselves do not require ongoing maintenance. Now, if we look at the turndown ratio between a traditional VAV damper and a Phoenix controls valve, they kind of look inverse of each other. So if you look at how a VAV box works, which is that black line, the way that they typically function is when they're in shutoff mode, as soon as they crack that blade open in the ductwork, you're going to get about 30% of your airflow. So it has what we consider a quick opening characteristic. And then really what you have is controllability between about 30% airflow and about 70% airflow, maybe a little bit higher. And that typically gives you about a 3-to-1 or a 4-to-1 turndown ratio on a VAV box. And also when you get down into the low end of the airflow range, the accuracy is going to get much worse just based on the velocity pressure in the ductwork. Now, if you look at that red line, that is indicative of how a Phoenix Controls Venturi valve works. It's basically an inverse of the flow curve that you would have with a traditional VAV box. And again, that's because it's a completely different technology using Bernoulli's principle and the Venturi design inside the valve. Pressure does not affect how the Phoenix Controls accuracy works. So once you take the pressure out of the equation, we can get very finite measurement across the entire flow range of that valve when we're calibrating it, so that when it gets out in the field, you get that 20-to-1 turndown ratio, which is useful not only in rebalancing buildings in the future, but also giving you the flexibility of turn down at night and running it full time in the daytime to make sure that you still have the ventilation rates required. When it comes to the speed of response on the Phoenix valves, there's really two parts to this. The first is the speed of response to command change. So in a wet chemistry environment, a high-speed environment, what's important is making sure that your valves track exactly what's going on in the room. So if you think about using a fume hood in a wet chemistry lab, you basically want the valve to move as fast as the sash can. And there's some ambiguity to the standards that happen inside of wet chemistry labs. Usually people will say it's about a 3-second speed of response from the sash's last position, but 1 second is better. And the reason they have those 3-second or so is because they can't make the guidelines favor one manufacturer. And because Phoenix is the only manufacturer that actually gives you a 1-second speed of response from command change, they can't really write the guidelines to favor us. However, competition, when they talk about speed of response, they'll usually say about 3 seconds from final position of the fume hood sash, which means that we're still within the guidelines. But again, Phoenix controls 1 second speed of response to command change. What that means is when I move my fume hood sash, my valve is tracking as fast as that sash is moving. And by the time I stop moving my sash within 1 second, not only my hood valve is going to position to its final position without hunting, but my general exhaust and my supply valves inside that same pressurized zone are also going to achieve their set point and park without hunting at all. Secondary to that is the 1 second speed of response on pressure changes in the ductwork. And going back to the beginning of this presentation, when we talked about that pressure independent cone with the spring in it, that's what we're referring to 1 second speed of response to changes in ductwork pressure. So basically, individually or separately from the control platform that's telling the valve where to go, that cone, that mechanical spring inside of the cone is actually repositioning itself in real time to make sure whatever set point the valve is set at, you're going to get your airflow within plus or minus 5%. Now we realize that flow measurement has been around for a long time, and we want to acknowledge that flow measurement is in the field, but we also want to talk about why we don't do it as a company. So what flow measuring is, some type of sensor that measures a media, whether it's water, air, or gas, something like that. Again, in our field, it's air. Typically, they have some level of field calibration associated with them. So once they get installed in the ductwork, whatever conditions are going on inside the ductwork have to be accommodated for. So again, going back to if you have a bunch of elbows in the ductwork, you have to accommodate for that. If you have a lot of pressure drop after that airflow control device, you have to accommodate for that, and you basically tune it in the field using a K factor, which is setting it to the best condition you can while it's installed in the field. And usually there's some type of device to control the airflow. In these examples, these are some of the popular ones that are out there. You can see a flat edge blade damper, a bifurcated butterfly valve, and a couple of different variations of Venturi flow measurement with a blade damper that's out in the field right now. So different factors that affect airflow measurement and why Phoenix doesn't measure flow. So we talked about with a Phoenix valve, you don't need straight duct runs. Well, in order to get an accurate measurement and an accurate flow control inside of a flow measurement device, you have to have straight duct runs. You're always going to have a reduced speed of response because you have measurement delays. There's always going to be a level of field balancing involved in this, which is going to take considerably more time to start up, which also means that there's going to be maintenance, there's going to be accuracy shift over time, and there's going to be drift over time. So let's take those three pieces one at a time. When we talk about installation issues, ASHRAE fundamentals state that in order to get the most accurate flow measurement out of one of these control devices, you need about 7.5 to 10 duct diameters of straight duct. So looking at this example, if we're using a 10-inch duct, that is 10.5 feet of straight duct, or 10 inches, times 10.5 duct diameters. So over 100 inches of straight duct to be able to get this flow sensor to work properly. Now, we all know in buildings that's pretty rare to get that much straight duct. Typically, you might get 1.5 to 3 duct diameters on either side of that flow measurement device, and that's obviously going to reduce the accuracy of that particular device. Now, when it comes to field balancing, you can see in this example that the red and the blue lines that are shown there, that's actually the flow profile of the air going through the ductwork at two different velocities. So in looking at that, the way air tends to flow in a system that has an elbow, air wants to travel in a straight line. So the air will go up the elbow, it will actually stick to the outside of the elbow, and that's why you kind of have that inverted S flow profile where you have a lot higher velocity on the outside of the elbow or the outside of the ductwork, and on the inside of the elbow or the inside of the ductwork, you actually have some reversion or backwards flow. Now, if you're taking an average flow velocity with that flow profile versus a nice fixed one that's in a straight piece of ductwork, obviously there's going to be an inconsistency. So what you see that little chart on the bottom there, it's actually looking at the inconsistency of flow measurement as the velocity changes through the ductwork. You can actually see that the pressure, the velocity pressure is spiking through that device, and it actually causes delays and it causes hunting in those type of control devices. So speed of response on these type of devices, again, will never be as fast as something that's using position-based control, because in this particular environment, you have to measure the velocity going through the ductwork. You have to record that velocity, do a calculation on where it falls in my flow curve, and then you actually have to readjust the damper position. So this is happening in real time. Velocity pressure changes, the controller takes a reading, the blade repositions the flow. Now I have a new pressure reading that then goes back to the controller, and I have this cyclical motion where I'm reading, repositioning, reading, repositioning. And typically that'll give you about a 2 to 3 second delay if you want quick controllability. But if you're measuring airflow and you want fast control, what it's going to give you is unstable airflow or unstable pressurization control in the room and in the ductwork. So every time that VAV box blade changes position in the ductwork, it's going to actually change the velocity, which makes it react, take another measurement, and then readjust. We call this hunting, because effectively, even if you have a VAV box set at a constant CFM value, it's always going to be moving to try to maintain that set point. And again, that's what you can see on the right-hand side of the screen with that blue chart. It's actually looking at a flow reading of a device over time, or pressure trend of the room. So it's looking at every time that blade damper moves back and forth, the pressurization is going to change inside of that space. Now, if you want better controllability of that space, you can obviously slow down the PID loop inside that device and give it a more deliberate motion. That will give you much better stable pressure control, and it won't hunt as often. However, when you have a rapid drop in static pressure, say when a building goes from unoccupied to occupied mode, you're going to have a large drop or a longer time for that device to actually catch up to that drop in static pressure. So if you slow down the control loop, you get more deliberate control, you get less hunting, but that also means when you have system changes, it's going to take a lot longer for your building to react. I've actually talked to some people that say they give about 30 to 45 minutes for their system to be able to change pressure when they go from occupied to unoccupied. So if the building goes occupied at 8 o'clock in the morning, they start the transition at 7:30. So the fans and all the VAV boxes have a chance to settle out before the occupants come in, and they get their comfort control up to where it should be. So it does cause some problems inside of a building just to slow down the control loop to get more stable control. Now, when you're talking about other critical environments, this is actually looking at an operating room inside of a hospital. This study was done between how a VAV box works and a Venturi valve or a Phoenix valve inside the operating room. Basically, what was trended was the differential pressure inside of that space. So looking at the pressure across the door. And in normal operating mode, the Phoenix Venturi valves had a standard deviation from 0 to 0.01 inches water column across the door. Now, if we contrast that to what you see with a VAV box or a damper set at constant volume, the standard deviation was twice that. It was from 0.01 to 0.02 inches water column, which is actually a pretty large deviation. And what they found was, in order to maintain the correct differential pressure across the door, you had to run the VAV boxes with 2 additional air changes per hour to achieve the differential pressure you needed and maintain that offset across the door. And if you look at that chart on the bottom of the screen, what those additional 2 air changes per hour cost is about $4,000 per year for thermal utilities for different climate control zones. And again, different, if you have city thermal utilities, campus thermal utilities, or self-generated, obviously the costs are going to be different. But if you look at that, for each individual pressurized space, you're saving at least $2,000 a year just by using Venturi valves to do the same type of airflow control. And in addition to that, we also had better infection control because we don't have that pressurization flipping across the door. Now, I mentioned maintenance, accuracy, and drift when it comes to VAV boxes, and these are really the big key items that we talk about. So what does maintenance mean? Well, it's wasted energy and something called turndown phobia, which basically means when I set my rooms from occupied mode to unoccupied mode, there is a chance that my pressurization could switch. And in that particular case, I can't have pressurization switch when you think about operating rooms or really critical environments with patients or things like that. So instead of turning down the space to save energy, they just leave the building running at full occupancy. Again, in an operating room, take 15 to 20, 25 air changes per hour, where they could turn it all the way down to 4 or 6 or 8 air changes per hour and save all that money when they're not occupied. They tend to just leave them running. So the accuracy we talked about, Phoenix products, plus or minus 5% across the entire flow and pressure range. But when you're talking about airflow control devices that use flow measurement, not only you're not going to get 100% repeatable airflow, but being able to measure and quantify the accuracy is very different than what you have with a third-party certified device like a Phoenix valve. And the last thing is drift, the inability to maintain set points, which will lead to inadequate pressurization control, and eventually you'll have to replace components like pressure transducers and recalibrate things year over year just because the drifting system. So let's take a look at these one at a time. So maintenance. If you look at these 3 airflow control devices, the one on the left is a supply VAV unit, and the 2 in the middle are exhaust VAV units. Will these VAV boxes be energy efficient? And the answer is no, because what typically happens is when the flow sensors get clogged up, they kind of have an inverse relationship to how much dirt is on them. So the dirtier they get, in the case of an exhaust valve, if the lint clogs up the flow sensors, that exhaust valve is going to go open. And if you have a situation where you have a supply VAV box tracking an exhaust box, as that VAV box goes open, it's still reporting a low flow through it because the sensor is still clogged. So if your supply valve is tracking that low flow from the exhaust valve, your supply valve is going to track to a low flow. Meanwhile, your exhaust box is going to be 100% open. So in these particular environments on the exhaust side, trying to maintain differential pressure across a door is very difficult because once the sensors get clogged up, the box works inversely of what its reading is. It's reading a low flow and it's going open to accommodate that change. However, it's not actually showing you what's really going on. People sometimes say, I like a flow measurement device because I know what's going on inside my space. But in these particular environments, you really don't know what those devices are flowing because the flow probes are completely clogged. We can look at some other scenarios. This particular valve was a clean, quote unquote, general exhaust valve in an animal holding area. And what you see on that flow sensor is actually the dirt and the dust and the lint that's in the clean air for the general exhaust air. This is not the cage rack exhaust valve. This is just general exhaust, clean air. And that sensor got clogged up in about 9 months of normal use, just taking animals in and out of their cages, giving them their shots and putting them back in. So you can just imagine how that would work after 9 months. Obviously that valve is going to be 100% open, so you're not going to be able to maintain your pressurization inside that space. Now, if we look to a different environment, this is a clean flow sensor inside of a patient room in a hospital. This is the same flow sensor after about 9 months of patients coming in and out of that room, the staff changing the bedding in that room and having visitors come in with dirt from outside the building. Obviously, when somebody comes in and visits somebody in the hospital, they're not making them take a shower and change into clean scrubs. So people are bringing in all that dirt from the outside world, and it goes through the exhaust ductwork or the return ductwork. And again, in this particular case, after about 9 months, that flow sensor was completely clogged up, which meant that that patient room was negative when it was supposed to be neutral. Not only are you wasting energy, but you're robbing air from somewhere else in the building. Now, when you look at different technologies, it's not just a flow cross or an orifice ring that can get clogged up, but when you look to vortex shedding, this is another product that it's a different approach to measuring airflow than a traditional flow cross. However, you have an obstruction in the middle of the ductwork that can still catch debris. And we have in this particular picture, there's a tissue stuck on that sensor, which does happen in fume hood environments. People take Kim wipes and tissues and throw them through the ductwork, and they're going to get stuck on anything that's sticking out in the middle of the ductwork. This is another example of a general exhaust valve or a general exhaust flow sensor, same type of vortex shedding technology. And what happens is when you get a lot of buildup on that sensor, not only can the pressure ports on that thing get clogged up so you can't read it, but as you change the diameter of that tube, it's going to change the velocity of air going through there, which is going to put an offset on your accuracy. Speaking of accuracy, looking at a typical pressure transducer, and for this particular example, I'm looking at what would be a 10-inch duct with a 1.5-inch pressure transducer boasting 1% full-scale accuracy. Now, salespeople tell you 1% accuracy is better than Phoenix Control's 5% accuracy, but what they miss is that little FS, or full scale. So what that attributes to in this particular range, and I apologize, it's kind of an eye chart there on the bottom of the screen, but the pressure range for this pressure transducer is 0 to 1.5 inches water column with a 1% full scale accuracy. So what that 1% full scale accuracy means is 1% of 1.5 inches water column is your fixed error. So if you look in the middle of that chart, it says XDCR or transducer error is 0.015. That is 1% of 1.5 inches water column. And that's important to keep in mind. So now if we look at the chart there on the bottom, what we're actually measuring with a pressure transducer is the velocity pressure. And that's calculated by the volume of the ductwork, or the area of the ductwork, and the velocity pressure. So if you look at the volume of air, 1,000 CFM going through a 10-inch ductwork, you can calculate out that the velocity is 1833 feet per minute. And the velocity pressure is actually a function of a square. And this is where a larger error comes into play, even with a 1% accuracy pressure transducer. So at 1,000 CFM, my velocity is 1833. My velocity pressure is actually the velocity of the air divided by a constant of 4,005, and then that number squared. So the velocity pressure at 1,000 CFM is 0.2095. If I add my transducer error onto that, my measured velocity pressure is now 0.2245. My measured velocity is 1898. My measured CFM is 1,035. And that's a 4% error at 1,000 CFM, which doesn't look too bad. But now if I try to get 2-to-1 turndown ratio out of that same device, I go from 1,000 to 500 CFM. My velocity pressure drops down to 917. My actual velocity pressure, which is 917 divided by my constant of 4,005 squared, is 0.0524. And my fixed transducer error is still there. So when I add my transducer error to my actual velocity pressure, my measured velocity pressure now is 0.0674. Measured velocity is 1040. Measured CFM is 567. So now at a 2-to-1 turndown ratio, I dropped from 4% accuracy down to 13% accuracy, which could put you outside the realm of being able to control differential pressure or offset inside of a space. And just like the same calculation, if I try to get a 5-to-1 turndown going from 1,000 to 200 CFM, again, my velocity drops to 367, which there's kind of an industry standard of around 450 feet per minute is really where the bottom of measurement capacity is. So this is really stretching it anyway, but for the benefit of the calculation, we'll go through it. So 200 CFM, my velocity is 367. My measured velocity pressure, which is 367 divided by 4,005 squared, is 0.0084. Now, if you look at the velocity pressure versus the error, those two numbers are getting very close to each other. So when you add the error onto the velocity pressure, my measured velocity pressure is now 0.0234. My measured velocity is 612. Measured CFM is 334. And now I have a 67% error on my airflow control. So in this particular device, if you wanted to maintain about a 10% accuracy, you can only get about a 2-to-1 turndown ratio. Once you go to a 3-to-1, 4-to-1, 5-to-1 turndown, and you get below that 5 or 400 CFM range, your accuracy is going to drop off to an unacceptable range. Now, in addition to that, that is with a brand new, fully calibrated pressure transducer. One thing that's never really talked about on the bottom of that specification chart is a thing called span shift. The way I like to talk about span shift in a pressure transducer is if you think about a balloon. When you take a brand new balloon and you inflate it the first time, it's not very elastic. So it takes more pressure, it takes more effort to be able to blow it up the first time. Well, after you let the air out of that balloon, every time you inflate it and deflate it, it's going to stretch more and more. Pressure transducers have the same thing happen, whether it's a rubber pressure transducer, plastic, silicon, glass, or some other media, metal that's in there, they all react the same. Depending on the accuracy of the sensor and what it's built with, obviously you're going to have a smaller shift over time, but every single pressure transducer, if you look at the data sheet for it, is going to tell you an accuracy and a span shift year over year. So what that attributes to, if you had a 2% accuracy pressure transducer with a 2% span shift year over year, at the end of year 1, you'll be at 102% of your original set point. At the end of year 2, you'll be at 102% of 102%, and so on. So the longer time goes on, that drift is going to happen more and more, and after 5 or 6 years, it's far enough that you either have to recalibrate those transducers or you have to replace them. And this is where a lot of big airflow control companies get you with things like maintenance contracts, so that they go in and they recalibrate stuff annually or semi-annually and replace a bunch of stuff. They have those service contracts in place because they need to replace components, they need to recalibrate stuff. Going back way to the beginning of my presentation, I said Phoenix controls valves don't require that maintenance. So it saves you time, it saves you money on not having a service contract. And again, we do recommend doing an audit, but it's not the same thing as a service contract. Next, I want to talk about this thing we call the low pressure myth. So we have this literature piece out there called Don't Fall for the Low Pressure Myth. I highly recommend reading it if you get a chance. But what the low pressure myth is, it's actually a mindset that some people are trying to push on people versus a calibrated device that comes from the factory calibrated versus something that uses an ultra low pressure drop, or what they claim is an ultra low pressure drop. And they're citing ASHRAE 130 as the low pressure performance test. Now, ASHRAE 130 is one of those things we were not familiar with. We had to educate ourselves on it. And basically what ASHRAE 130 is, it's a test that measures the flow through a device when it's fully open. So if you think about a VAV box, you fail the device fully open, so the blade is parallel to the ductwork, so there's very little obstruction in the ductwork. And then you put a pressure on the inlet side and you measure the flow coming out of it. And basically that gives you the lowest controllability or the lowest flow that you can get at that pressure, but it doesn't really tell you that the device is in control. So ASHRAE 130 pressure drop with a Phoenix valve versus other devices or third-party VAV boxes and things like that is similar because it's based on the physics of airflow. Basically, the only thing creating an obstruction or increasing the pressure per an ASHRAE 130 test is what's inside that valve. So Phoenix has a cone inside of the valve. Other devices like a bifurcated butterfly damper has a big section or a static regaining compression section inside the valve. The only thing that changes pressure drop through a device that's fully open is what's inside the valve, the area that's being taken up in the dead air space of the valve. So what we claim as Phoenix controls, and what we've proven time and again, is that Phoenix has the lowest controllable pressure drop available. And that means when we say we're plus or minus 5% across the full flow range and pressure range of the valve, we have the lowest pressure drop to be able to stay at that plus or minus 5% accuracy. It doesn't matter if a device flows air when it's fully open. If you don't have some obstruction inside the ductwork to control the flow, you're not really controlling anything. So it just basically means ASHRAE 130, I want to know what flow I can get at a given pressure. I fail my device open, I measure my flow, and that's what I put on my data sheet. But the problem with that is the low differential pressure design when wide open does not translate to low pressure control. So if you try to control pressure with a given accuracy at those low differential pressures, most of the time the competitors that are claiming these ASHRAE 130 low pressure drops have an accuracy range of about plus or minus 15%, because just like those flow measurement characteristics that have a low accuracy with a high turndown ratio because of that transducer, you still need a minimum velocity and minimum pressure to be able to control to an accuracy level comparable to what Phoenix Controls has. So many manufacturers state their low pressure when it's open, but they don't state the pressure required to be in control. One other thing to think about, ASHRAE 130 devices, when they put those flow numbers inside of their chart in their sales literature, they're talking about being full open position. Well, if you go back to ASHRAE 90.1 standards, which is trying to reduce your fan pressure to its minimum, get your brake horsepower, your fans down to its minimum, ASHRAE 90.1 states that the devices cannot be 100% open. So if you're adhering to ASHRAE 90.1 to get your devices within that controllable range, they cannot be 100% open. Therefore, they will never run at the low pressures that are stated based on the ASHRAE 130 guidelines that they put in their ordering guides. Lastly, I want to talk a little bit about how the Phoenix Controls network architecture works. And this will kind of go through a system from bottom to top, from the valve level all the way up to the building automation system. So if you look at the Phoenix system, on the bottom of the screen there, we have a line that has a view backnet monitor, which is a native MSTP device, and then we have tracking pairs with our Traxcell or Theris valves. Now, the Traxcell and Theris product line, which is for our non-fume hood research environments or for our healthcare environments, you can get those either in a direct lawn connection or a direct backnet connection, which can go typically correctly on the backnet MSTP network inside of a building that goes to the building automation system. So for those devices, you have a choice to have native MSTP or native LAN that can go directly on the building backbone. And in that particular case, we don't need any type of an integration device. Now, if we look on the system above that says fume hood valve with Solaris valve controller, those Solaris valve controllers use a proprietary network architecture, and that's to communicate between the fume hood valves, the supply valves, and the general exhaust valves, as well as the fume hood display that's controlling what's going on those wet chemistry fume hoods. So in that particular environment, we need a device to convert the data from our proprietary network up to the building automation system. So in that particular scenario, we use what we call a PCI 8000. And that's a Tritium Niagara based product. It's doing protocol translation. It's also doing houses the database for all the devices inside of the room, and it has some test and balance tools built into it, as well as some diagnostic web pages. So when you're using our Solaris system, that's typically needed to put that information on the building automation system. And then above that, we have some different software. So there's a room manager piece of software, which is a customer-based piece of software to manage their entire site once it's been commissioned. Vision, which is a full front end that I mentioned way back at the beginning of this presentation, that gives you the analytic capability, the trending capability. It gives you some graphs to show you what your energy usage is in your space, how you can reduce your energy footprint. It's kind of a critical front end solution, but it's not meant to replace 100% your building automation system. So we call it the Vision Critical Environment Solution, or the Vision CE, and that gives you a look into everything in your critical environment system. It can also pull in third-party BACnet data, not just Phoenix systems. So if you had fans or you had some kind of a CO2 sensor, TVOC sensor inside the space where the Phoenix equipment is, all of that can be merged into one front end with the Vision software. And then in addition to that, the Workbench software, that's what the Phoenix technicians use to commission and manage the site from a management standpoint. So when we look at Phoenix system benefits as a whole, we provide the safest, most comfortable environments. We have reduced costs for mechanical systems with no maintenance. We have the lowest installation costs over time, the lowest energy costs with the greatest turndown, and the greatest controllability inside of our valves. We have industry-leading sales and support channel, which every single Phoenix representative is trained at the factory for both sales and support side. And we integrate with all BMS partners through that Tritium Niagara system that we use.